chapter 14, part 3. So I just want to mention quickly here, briefly, about the relationship between rate and temperature. It's really very important. So when I said earlier on that if you have a K value that's always constant, that's true if your temperature is constant. K will change with temperature. And so this Boltzmann distribution curve more or less explains why K changes with temperature. And we know that in general, as temperature increases, rates of chemical reactions will increase. And it's really due to the distribution of molecules that have the needed kinetic energy for the reaction to go. So at a lower temperature, we can see that there's a high concentration of molecules that have a specific temperature within a specific kinetic energy range. But as you have a higher temperature, that's what this curve represents, is the higher temperature, then you have a greater distribution of molecules that have the needed kinetic energy, which right here we could identify as, say, the threshold of energy that's needed. So while the area under each curve for the low temperature and for the high temperature is the same, it's the dispersion or the variety of kinetic energies that the higher temperature molecules hold that allow the reaction to occur faster. And so what I want to point out down here is really just the equation that shows the relationship between the rate constant K and the temperature. So the ratio here of the rate constant 1 versus rate constant 2, or the natural logarithm of that ratio, is equal to E sub A, which is the energy of activation. E sub A is called the energy of activation, and I'll talk about that on the next page. So that energy of activation over a constant R, which would be given in an equation, it's 8.3 joule per mole Kelvin. 8.31 joule per mole Kelvin, is equal to 1 over the temperature 2 minus 1 over the temperature 1. So this equation here will show you, as temperature changes from T1 to T2, how the relationship between your rate constants also change. And so here is another equation that you might find, which would help you determine what the rate constant is at one particular temperature. But in order for you to use this equation, you would have to know this constant, which is called the frequency factor, which is how frequent the molecules collide with one another. This equation is not used quite as much. We won't use it at all in our problem solving. This one, though, is a very common equation that you should know. Well, you can always have the equation with you. So the other thing that I wanted to talk about was this energy path diagram that will help us understand the next and last section of this lecture. But if I have reactants, and this of course would represent an exothermic reaction because the energy of my products is lower than the energy of my reactants. And so you're going to have this energy of activation, which is going to be the energy difference between where the reactants begin and where what we call the activated complex forms. That value between the start and the peak is called the energy of activation. And the activated complex is really an intermediate product. It doesn't last long, and then the reaction progresses to form the products. And so the distance between where the products form and where that activated complex formed would be the energy of activation of the reverse reaction. And then the difference between where the energy that the reactants have at the beginning and the energy that the reactants have at the end is the delta H. And that all comes from your chapter 5 for your delta H and your reaction pathway. So this here just shows you how to calculate delta H using the energy of activation values. So I'm going to stop.